colder ambient at T infinity. Hot gases at Tg, colder ambient at T infinity. The heat transfer is happening through that composite slab in this direction Q. Okay. There is a composite slab made up of two materials, okay, having the conductivities K1, K2. One side of the slab is exposed to the hot gases at Tg, and the other side of the slab is exposed to the colder ambient fluid at T infinity. Tg is much greater than, far greater than T infinity. Some flue gases are there. Hot flue gases are generating the heat. Now, I would like to calculate what is the rate of heat transfer. Rate of heat transfer in what? Between the hot gases and the colder ambient fluid, and how to calculate the junction temperature. Okay. Assume steady state one-dimensional one-dimensional conduction convection heat transfer through composite slab. Assume steady state one-dimensional conduction convection heat transfer through composite slab. So, the main heart of the problem is construction of the thermal circuit and its understanding. In any heat transfer problem, particularly in this chapter of conduction, one must clearly understand what is the thermal circuit and how to calculate the heat current. Okay. So, the thermal circuit looks like this. How many resistances there? Means what is the mode of heat transfer between the hot gases and this side of the slab? It is by convection. The mode of heat transfer is by convection, right? Because between the hot gases here, that will happen by the mode of heat transfer occurs by convection. So, whenever there is a convection, how do you notify that? With a given value of the convection heat transfer coefficient. So, there is a convection here. There is a conduction here, there is a conduction, and again this side there is convection with H2. Convection, conduction, conduction, and again there is convection. So, you speak of convection, H is always a given parameter. Particularly in the conduction chapter, you are talking about convection, H is a given parameter. But later when you enter the convection chapter, our main focus would be how to calculate that convection heat transfer coefficient from a given data of the solid body and the fluid flow. We will be calculating how to get that H. So, in entire convection chapter, our main focus will be how to calculate that H value. But in the initial chapters and initial topics of conduction, you speak of the convection wherever it is spoken. H is always a given parameter, which is a convection heat transfer coefficient, also known as the film heat transfer coefficient. Look at the units there, watt per meter square Kelvin. Okay. So, the thermal circuit contains how many resistances? Convection, conduction, conduction, and again convection. So, the thermal circuit comprises 4 resistances: convection, conduction, conduction, and again convection. Tg and T infinity. So, will be the temperature profiles will be like this. Why it is a curvilinear like this, you will come to see. You will come to know only when I teach the thermal boundary layer concept in the convection. So it is a curvilinear here, straight line, and again curvilinear. This is the temperature Tg, this is T infinity. This temperature is T1. What is the T1? The left hand side, leftmost temperature of this composite slab. This is T2, junction temperature. This is T3. Okay, Tg, T1, T2, T3 and T infinity. Tg is the temperature of the gases, and this is the T infinity is the temperature of the colder ambient, maybe atmospheric air. So first convection, conduction, and again by convection. What is the first resistance? Convection thermal resistance 1 upon H1A. 1 upon H1A. That is the first resistance, convection. Then you will have the conduction resistance B1 by K1A. Then you will have the conduction resistance B2 by K2A, and finally we will have the convection thermal resistance 1 upon H2A. Okay, the flowing current is Q. The rate of heat transfer between the hot gases and the ambient colder fluid. Tg is much greater than the T infinity. So the mode of heat transfer is like this. First by convection, conduction, and again convection. Totally there will be 4 resistances. Convection resistance left hand, right hand sides, and in between we have the 2 conduction resistances. The flowing current is rate of heat transfer by Q. Therefore, rate of heat transfer between hot gases and ambient fluid the total thermal potential Tg minus T infinity divided by sum of all the resistances. All the resistances are in series. Therefore, what is the total resistance? Sum of all the resistances. And mind that the area of heat transfer is not changing in the direction of the heat flow. I already said the main character of the heat transfer through a slab is the area of heat transfer will not change in the direction of the heat flow. But later when you come across the different geometries like say radial heat transfer through a cylinder, radial heat transfer through a hollow sphere, there the area of heat transfer changes. In case of the slabs only, the area of heat transfer will not change in the direction of the heat flow. Okay? That is why I am not writing A1, A2 like this. And I already said in case of the slabs, most of the occasions, majority of the cases, we will write the heat transfer rate per unit area, which we call it as the heat flux. Therefore, heat flux will be heat flux means heat transfer rate per unit area. Q upon A will be Tg minus T infinity. Tg is the temperature of the hot gases divided by sum of all the resistance per unit area. Heat transfer rate. Heat flux means what? Heat flux or the heat transfer rate per unit area, both mean the same. This flux is the word which you see only in this subject, heat transfer subject. Heat flux or heat transfer rate per unit area. B1 by K1 plus B2 by K2 plus 1 upon H2. This H1, H2 values will be definitely different, even though fluid is same. Supposing this side fluid and this side fluid is same, but still If it is a forced convection, if it is a free convection, H values will be different. H value is not a property of the fluid, not a property of the solid. H value depends upon few thermophysical properties only, rho, mu, Cp, K. But H itself is not a property of the medium or the material. So heat flux means what? Heat transfer rate per unit area. Whenever you see the flux, these units you will come across what? Per meter square. So this is the how we calculated the heat transfer rate per unit area through the composite slab with convection on both sides of the slab, right? Now, whenever there is such a multi-mode heat transfer is there, multi-mode means more than one mode. There is more than one mode here. There is conduction here, there is conduction, but other sides you have the convection. Whenever there is a multi-mode heat transfer, sometimes radiation also may be there. Radiation also may be there. All the three modes of heat transfer, sometimes they may exist. But generally in our gate problems, in our analysis, usually we come across two modes of heat transfer at a time. So whenever there is such a kind of a multi-mode heat transfer is there, multi-mode heat transfer is existing, we will bring in one important coefficient called overall heat transfer coefficient U. It is indicated as U. Let me define that. What is the meaning of that overall heat transfer coefficient? This U and H would have the same units. What is the definition of this U? U is the parameter which takes into account all the modes of heat transfer into a single entity. Though it is having the same units as that of H, even though U has got the same units as that of H, H speaks of only convection, but this U talks about, look at the word there, overall. Overall means all the modes of heat transfer effects are put into one nutshell. So I could define U as the parameter which takes into account all the modes of heat transfer, conduction, convection and radiation, if it is existing, into a one nutshell, into a one entity, and thus it indicates the total thermal resistance offered by all the three modes put together. That means if the total resistance is more, this U value will be lesser. If the total resistance, that composite, everything, all conduction, convection, resistance, earlier I had given, if that total resistance is lesser, this U value will be more. U is the parameter which takes into account all the modes of heat transfer into a single entity and hence is defined from the equation Q is equal to UA delta T. U is the parameter which takes into account all the modes of heat transfer, into a single entity and hence is defined from the equation Q is equal to UA delta T. Sometimes I am write the Q like this or this way also. Sometimes I am writing like this, anyway it does not matter, that both mean the rate of heat transfer, UA delta T. U and H have the same units. This U is the parameter very often you see in the almost every problem of heat exchangers. In heat exchangers, in every problem of heat exchangers, like whether it is a LMTD method or a effectiveness NTU method, log mean temperature difference method or NTU effectiveness method, in both the methods, the U is a compulsorily used parameter when you are doing any heat exchanger problems. Later we will see in the heat exchangers chapter. That is watt per meter square Kelvin. This is the units of U, right? And this delta T is the where, what is this delta T? Where delta T is the total temperature difference in the entire thermal circuit. Total temperature difference in the entire thermal circuit. Now, if you just take this equation as 2, if we just take this equation as 1, if we just take this equation as 1 and this equation as 2, comparing 1 and 2, we get 1 by U is equal to 1 by H1 plus B1 by K1 plus B2 by K2 plus 1 by H2. This is the formula for the U. Mind that U and H will have the same units. And one thing I would like to tell is that if the total thermal resistance regarding the U, I would like to give this point. If the total thermal resistance in entire circuit is lesser, in entire thermal circuit, if the total thermal resistance in entire thermal circuit is lesser, then U value will be more. Then U value will be more. If the total thermal resistance in entire circuit is lesser, then U value will be more. That I can say this U talks about what would have been the relative magnitude of the total resistance. Look at the name of it, name of U, overall heat transfer coefficient. If the U value is more, it means that from the definition, if U is more, rate of heat transfer is more. That means the total thermal resistance against the heat flow would have been lesser. Okay? U and H will have the same units. That point also you have to keep in mind. The delta T is the Tg minus T infinity. You can see here the delta T is Tg minus T infinity. That Q is equal to UA, the total thermal resistance, the total thermal potential we can say. The total thermal potential Tg minus T infinity must be taken to define the overall heat transfer coefficient. But basically, U will take into account all the resistances into a one nutshell. I mean, if the U value is more, the total resistance against the heat flow would have been lesser. U simply talks about every resistances it will put into one nutshell. If U is more, total resistance will be lesser. Okay, now let me do some few problems there. Thermal conductivity is lower for air and what? In fact, water is definitely more conducting than thermal conductivity of water is definitely greater than the thermal conductivity of air. Liquids have got more conductivity. And the answer for this question is, answer is B. Among the four, air is the least thermal conductivity, 0.026 or 0.025 watt per meter Kelvin. Water vapor, saturated water vapor, slightly more conducting than air. Generally, I am not advising you to remember all the conductivity values, but most of the important fluids like water, air, some mercury, aluminum, some copper, you should at least try to remember what is the relative magnitude, relative values of the K. Sometimes they will give you 4 materials. He will ask you to arrange either ascending order or descending order of K. I have seen many questions in the GATE also. So have some idea about which materials have got more K, which have got lesser K. I told you earlier classes also the conductivity of the gases is very low. Liquids have more conductivity. Metals and crystalline materials like diamond, quartz, etc., they got very high thermal conductivity. You know, refractory brick, grass wool, asbestos, etc., they are the insulating materials. Obviously, they have the low K. So, which has got relatively more, which has got lesser, try to keep an order of magnitude relatively in mind. Relative magnitudes, try to remember them. Look at this, for a given heat flow and for the same thickness, the temperature drop across the material will be maximum per. Thickness is asking, means it is a slab. Q is equal to Ka delta T by B. It is also a previous gate question. Most of the questions which I am solving, I have picked up from the majority of them from the previous gate paper. Some of them from the engineering services papers also have included. Some preliminary exams of the engineering services. Okay. Previous papers of IES and previous years of GATE, I am picked up some important models, I am solving them. And for a given heat flow, Q is fixed, and for the same thickness, B is also fixed. B is also fixed. B is the thickness, right? He is asking about delta T across the material. Delta T is maximum from that given equation when obviously when K is minimum. So which material has got the minimum K among all those? Glass wool. Answer is C. Glass wool has got a K value of 0.075. That refractory brick around 0.8 or 0.9, that refractory brick. So if we just look at the descending order, their K of the copper is greater than the K of the steel, greater than the K of the refractory brick, greater than the K of the glass wool. This is the descending order of the K. Of course, these two are the insulating materials. These are the metals. Metals are the very good conductors. So answer is C. He has asked the descending, it is also previous gate question. In descending order of magnitude, conductivity. Okay. Iron, liquid water. Iron is a pure iron, is a metal. All metals possess good conductivity. So A, descending order, A greater than liquid water, saturated water, A greater than, aluminum is highest. Aluminum is high, 200. Pure iron has got only conductivity of the pure iron is around 50, K of the aluminum is around 200. Aluminum is an excellent fin material because of its high conductivity and low weight. Aluminiums are very commonly adopted fin materials because of its low density, low density and very light material and having a very good conductivity. Water vapor is almost same as air. Air and water vapor, their conductivities are almost equal. So answer will be D, greater than iron, greater than liquid water, that is B, and least is C. DA, BC. Answer is C. C is the answer. This is the descending order. Look at this. In a composite slab, the temperature at the interface between the two materials, this one, see this. This is the, the temperature at this two materials here is equal to the average of the temperature at the two ends. That is, he has given that T interface at the junction temperature is the average of the, it is a given, okay. Then which of the following answers will be valid given that? So the first, let me construct the thermal circuit. thermal circuit has two resistances T1, T2, this is T inter. Flowing current is Q. What is the first resistance here? Because there is in they are in a series circuit. Series circuit means one after another. Series circuit means one after another. Current is flowing first through this slab and then through this slab. This is the direction of the heat flow, right? This is the direction of the heat flow. What is the first resistance? 2B by K1A. Second resistance will be B by K2A. Flowing current is Q. So Q is same throughout. Q is equal to T1 minus T inter this potential difference divided by this resistance is Q. What is this resistance? 2B by K1A. This is equal to T inter minus T2 by B by K2A. A gets cancelled, B also gets cancelled. And numerators also we could cancel off. Numerator also we could cancel off because he has given that T inter is a T interface. T interface is average of the T1 and T2. Okay. Therefore, implies we can write that by cross multiply 2K2 is equal to K1. Answer will be D. D is the answer. Actually, just by seeing the figure itself, just by looking at that figure itself, we can notice that K1 is greater than K2 because the slope is lesser, the slope is more. Definitely from the figure I can say that K1 is greater than K2. From figure itself we can judge. Given from the given figure, we can easily judge that K1 is more than K2. Why? This slope is lesser, this slope is more. This slope is lesser, this slope is more. Therefore, when the slope is lesser, conductivity is more from the figure. But he has asked the exact relation. So, answer is D. K1 is to K2. Actually, sometimes there may be an arrangement of parallel. Like for example, sometimes the situation may be like this. There are three materials A, B, C. If this is the Q, then the heat will be conducting simultaneously through both the materials like this and like this, right? Simultaneously heat will be conducted. Then the thermal circuit will be first resistance is A, then the resistance will be B, and then the resistance will be C. Okay, this is the resistance of A, this is the resistance of B, and these are parallel, no? This is a heat resistance, they are in resistances are in parallel. Now in such case we can calculate that equivalent resistance as 1 by RB plus 1 by RC. Note when the two resistances are parallel, we can calculate the equivalent resistance, and this will be combined to this to get the total resistance. We know that when two resistances are parallel, how to match them. Okay. So this is the parallel circuit and versus and the series. Heat will flow by first by through the A, and then heat will be flowing parallel in these two parallel resistances. This is a Q current QB. This is current flowing through the C. Okay. So, this is the thermal circuit for the series parallel arrangement. As the temperature increases, the thermal conductivity of the gas also will increase. Yesterday, last class, I have shown you that variation also. For any gas, as the temperature increases, conductivity increases, viscosity increases, specific heat increases, but only one thing will increase, only one thing will decrease, that is density. When a gas temperature increases, conductivity, viscosity, specific heat, all three will increase, but density of the gas will decrease. But somebody may ask, what would about the liquids there? Generally, for liquids, for most of the liquids, as the temperature increases, thermal conductivity will decrease. But few exemptions are there, like water and glycerin. For water and glycerin, first conductivity will increase beyond some range as the temperature increases. As the temperature increases, for water and glycerin, for some temperature range, that will heat conductivity will increase. After that, conductivity will decrease. But generally, you may remember that for gases, as the temperature increases, conductivity increases. For liquids, as the temperature increases, conductivity may decrease, except water and glycerin. For water and glycerin, first it will increase and then decrease. So, look at this problem. It is a previous GATE question only. It is given in the previous GATE examination. Consider one-dimensional steady-state heat conduction across a wall. This is a wall, across a wall. This is a 1 into 10 power 5 watt per meter square. Okay. This T infinity symbol given for the ambient temperature. Conductivity of the slab is given. The thickness is also given. Thickness is how much? The thickness is given as 30 mm. And the conductivity is at x is equal to 0, a constant heat flux of 1 into 10 power 5 watt per meter square is applied. On the other side of the wall, heat is removed from the wall by convection with a fluid at 25 degrees Celsius. Heat transfer coefficient is 250 watt per meter square Kelvin. Here there is a convection happening on the other side. The convection H will be 250 watt per meter square Kelvin. What is the temperature at x is equal to 0? What is the temperature here? So, now between, if you just take this, that means he is asking what is T1. He is asking what is the T1. Between T1 and T infinity, how many resistances are there? One is conduction here. There is a conduction, no? There is a conduction here. And then here we have the convection between this surface and the fluid. This is a fluid. Between a solid and fluid, what is the mode of heat transfer? Convection. So, between T1 and T infinity, between T1 and T infinity, if you draw the thermal circuit, there is one conduction resistance and there is followed by convection resistance. This is conduction, this is convection. What is the conduction resistance formula? B upon Ka. What is the convection resistance formula? 1 upon Ha. But he has given the per meter square. So, therefore, what is the area of heat transfer here? Area of heat transfer will be 1 meter square, because he has given the flux there. Look at this. He has given the flux watt per meter square. That means area of heat transfer is 1. So, this is the Q upon A. Therefore, Q upon A is equal to how much? He has given 1 into 10 power 5 watt per meter square heat flux is equal to T1. This is T1. This terminal is T infinity. So T1, what is the T infinity given? 25. T1 minus 25 divided by sum of the two resistances. A is taken as 1. What is the B value? 30, but that is given in mm. We have to convert into the meters. Remember, in entire heat transfer, all the dimensions must be kept only in meters. B upon Ka. What is the K there? K is given as 15 plus 1 upon H. H value is given as 250 watt per meter square. You will get the T1 so many degrees Celsius. I think 625 is the answer, I guess, but you can easily calculate that. It is a fill in the blanks question, numerical data, NDT type. In the gate there will be an NDT type. But while answering the numerical data type like fill in the blanks, be careful what are the units that has been asked in the question. Sometimes it may be asked in Kelvin. Look at this. Sometimes it may be asked in Kelvin. You will be getting the correct answer in Celsius. If you type the same Celsius, your answer will become wrong. So, the precaution regarding the fill in the blanks questions in the gate examination is what units he is asking the answer. That keep that. Suppose if you are getting the answer in Pascal, sometimes if you are asking kilopascal, though you got the correct answer, because of the wrong feeding, your answer will be wrong. You got the correct answer, but if you just don't observe the units, what is asked in the question, you will be typing the wrong answer, though your answer is correct. So, it is Celsius, I can keep in the Celsius. Sometimes he may ask Kelvin, we don't know. But be careful about that numerical data type questions. This is a very good question asked in the recent gate examination only. A slender rod, slender means thin, slender means in English thin, of length L, diameter D, L is far greater than D and conductivity K1 is joined with another rod of identical dimensions, but of the thermal conductivity K2 to form a composite cylindrical rod of length 2L. First let me draw that given question like this. A slender rod means thickness is diameter is small, of rod of length L is joined end to end. This is L, this is L. Okay, diameter is D. Okay, this conductivity is K1, this conductivity is K2, end to end 2. So you got a composite cylindrical rod of length 2L. The heat transfer in radial direction and contact resistance are negligible. That means there is no heat transfer in the radial direction. Read the problem correctly. The heat transfer in the radial direction is negligible. That means whatever the heat transfer happening, in what direction it is supposed to act, this is the direction of the heat flow. Because there is no radial conduction, heat conduction along axial only. How do you know that? He has clearly mentioned heat conduction along axial only, axial direction only. Okay, what is an effective thermal conductivity or equivalent? The effective thermal conductivity of this composite rod. Equivalent means, that means you have got a rod of length 2L, Q is passing. What is the Q equivalent or effective? Same, both mean the same. K effective or equivalent. Sometimes they also call it as the equivalent conductivity of the composite rod. When you talk about the equivalence, please remember that when you talk about the equivalence, what you have to compare is thermal resistance and area. Two situations, two geometries, two different geometries are said to be thermally equivalent in the heat transfer point of view only if the thermal resistances are equal between them and also the area of heat transfer is equal between them. I repeat once again, two different geometries or two different two different given geometries are said to be thermally equivalent in the heat transfer perspective only if the thermal resistance between them must be equal, number one. Number two, the area of heat transfer also must be the same. Is it the area of heat transfer same? Yes. This is the diameter. This is also the same diameter, right? So the area of heat transfer, this area of heat transfer is same here. That is one is satisfied. And by equating thermal resistance, you will get the, what is the thermal resistance here in this situation? L by Ka, B by Ka I have to write, but in place of B you have got the L. L by K1A divided plus L by K2A. This is the thermal resistance in this situation. Then what is the thermal resistance here? What is the total distance now? 2L by K equivalent or effective, anything is okay. Both the mean the same, K effective into A. Now equate these two resistances, you will get the K effective by equating thermal resistance between these two situations, that is L plus L by K1A plus K2A, by equating these two resistances, L by K1A plus L by K2A is equal to 2L by K effective into A. That A could be cancelled. This A could be cancelled that throughout. Now, what is the K effective? You can easily write that will become, L also gets cancelled in the numerator. So 1 by K1 plus 1 by K2 is equal to 1 by K1 plus 1 by K2, 1 by K2 is equal to 2 by K effective. So can easily, what is the answer then? So K1, K2 is the LCM here, K1 plus K2. So K1, it will go to that K1 plus K2 will go to the denominator here. That is 2K1, K2 by K1 plus K2. Answer will be B. B will be the answer. This is the answer. K effective will be. Please note that very important, this problem is very important because it is defining other way the equivalent thermal conductivity. Two different geometries are thermally equivalent if their thermal resistances are equal. Main important thing what I have done is, I just equated the thermal resistance because areas are also same. Look at this area and this area of heat transfer also same. That should be same. Then only that equivalence concept will be valid. I just equated the thermal resistance between these two situations. I got this answer B. Very good question which is asked about recent GATE examination only. This problem is also very easy. In a furnace, the inner and outer surfaces are given. Inner and outer surfaces 1100 and this is 200 given. Inner and out, and the brick wall is covered by insulating material. This is a brick wall and covered by insulating and material thermal conductivity K2. This is K2. Okay, thickness of the insulation is 1/4 of the thickness of the brick wall. That is L2 is 1/4 of the L1. The outer surface of the insulation is 200. The heat flux through the composite wall given, the value of the K2 is very simple problem which is also given in the recent GATE examination. Just construct the thermal circuit, you will easily get the answer. Very easy question this is. Just construct the thermal circuit. How many resistances? Conduction, conduction here, right? Only there is no mention of convection there. Only two resistances. Both the slabs are attached to one another. There is a series circuit. Q by A is given. Look at that. Flux is given. all the slabs cases is given the, you will give the flux only, majority of the problems. This is 1100, the other side is 200, this junction is 700, both are conduction resistance only. L1 by K1A, A is taken as 1 here because flux is given, no. What is other resistance? L2 by K2 into area. What is the area of heat transfer? 1. Why area of heat transfer is 1? Because flux is given. Flux means area of heat transfer is 1. So you can easily get the K2. Their current is same. Q by A is equal to 2500 is equal to 1100 minus 700 divided by the first resistance. L1 by K1 given. What is the K1 given? 2.5. Area is 1. This is equal to this potential difference divided by this resistance is current. And again this two potential differences I am writing separately. This is equal to 700 minus 200 divided by L2 by K2 into area. Now you can keep this situation given, you can keep it here. L1 you can keep it as the 4L2, that L2 gets cancelled, you will get the answer for K2. Very simple question. Okay, but round it off to 2 decimal. You have to keep, say for example 3.548 you got. You have to type that 3.54. In the gate examination, after decimal minimum 2 digits you have to type. The third decimal if you write, even if you write wrong also doesn't matter. First 2 after decimal, the 2 digits must be correct. Suppose if the K2 is 3.545, 54 must be typed correctly. The third decimal if you write or not write doesn't matter. Put this L2 situation, L2 as 1 by 4 of L, or rather this L2 is 4, or rather L1 is equal to 4L2 you can keep. This L2 is 4L2, right? That L2 gets cancelled, you will get the answer for K2. Such questions are very, very common in the gate examination. This is also recent gate question only.